Okay, so we're going to do some homework, Fred. Are you ready?
I'm ready.
Okay, how about you read that first one to us?
How much heat in joules and in calories? Are we going to be using calories?
Well, we won't be using calories in this class, so don't worry about those. But, yeah, we might do some, there's 4.184 joules for every calorie. So if you solve for joules, you multiply by 4.184 to get to calories. Solve for calories, divide by 4.184. Okay? So, yeah.
Okay, so how much in joules must be added to 75 gram iron block with a specific heat of 0.449 joule? No, what does that say?
4.449 joules per gram. All right. To increase its temperature.
Oh, it goes on?
Yeah, to increase its temperature from 25 degrees Celsius to 1,535 degrees Celsius. Okay, so this is a general question that, we always should be aware of how to answer, right? Any system, we want to know how much heat energy is required to perform, whatever job we want to perform. In this case, we want to raise the heat, and the amount of temperature change that we're after, you can always identify by taking the final temperature, 1535, and subtracting the initial temperature, 25. So that's 1510. So 1510, that's how many degrees Celsius we want to change the system. We also need to know the mass of the system that we need to change, okay? And it says that it's 75 grams, right? If we were heating a really tiny iron block, then it would take a different amount of energy than if we were heating a very large amount of block, right? So the amount of material that we're going to heat, call this the mass, right? This is the change in temperature that we're after. If we just want to change it 1 degree, then it's a little bit. But if we want to change it a lot, it changes the amount of heat energy required. Okay? And the other thing we need to know is the 0.449 here, which is the specific heat, which is how many joules it takes to raise a gram 1 degree Celsius. This should say joules per gram. Oh, it does. Degrees Celsius over there.
Oh, okay.
All right. So that is going to tell us how many joules of energy are required. Joules per gram degrees Celsius. What happens if I multiply these units, joules per gram degrees Celsius, by grams in degrees Celsius?
What do you mean?
Well, can you see? If the units for a specific heat are joules over gram degrees Celsius, and the units for change in temperature is degrees Celsius, and the units for mass is grams, can you see how the grams cancel out, the degrees Celsius cancel out, and I'm going to be left with joules?
Okay, yeah, I see that.
Okay, so that is what we're utilizing to remind ourselves how these numbers come together. So 75 times the change in temperature times the specific heat, 0.449, that is 50,849 joules, or 50.849 kilojoules. Okay, good. How much heat in joules and in calories is required to heat that much ice from negative 23 degrees Celsius to negative 1 degree Celsius? Okay, what do you think?
Well, do we know, can we do the same thing?
We can do the same thing. What are the things we need to identify to know how much energy it takes to heat a system?
Oh, it's mass. It's how much temperature change we want. So that looks like we want 22 degrees change, right?
That's right. Negative 1 is the final, minus the minus 23, that would be positive 22. We want a 22 degrees Celsius change. All right, and the mass of the material?
28.4 grams.
All right, so 28.4 grams. All right, now the specific heat. What's the specific heat?
Do we know the specific heat of all the materials?
That's a good point. We don't know the specific heat of all the materials. And so if we want to find a specific heat, we have to go to a table in a book, in our book, or online, a table online. It's fine. Excuse me. I'm going to go to a table that is online here. I'm just going to look for this specific heat of ice. Now, ice is frozen water. In class, and maybe in some of the homework or the quizzes that you've looked at, or whatever, if you've done any homework, the specific heat of water is 4.184 joules for every gram that changes a degree Celsius. But this is the water as a liquid. And it's different. The specific heat is different if you're dealing with a solid or if it's in the gaseous phase. So to find the specific heat of ice, we have to look it up. What's the specific heat of ice? It's
2.108 kilojoules per kilogram Kelvin. According to Topper, the specific heat capacity, or the amount of heat needed to raise the temperature of a specific substance in a specific form 1 degree Celsius, for water is 4.187 kilojoules per kilogram Kelvin, for ice 2.108 kilojoules per kilogram Kelvin, and for water vapor 1.996 kilojoules per kilogram Kelvin.
So, there it is, 2.108 joules per gram degree Celsius. So that's what I have to use here for my specific heat. So 28.4 times 2.108 times 22, and that gives me 1.317 kilojoules of energy. Okay? Number 8. How much would the temperature of 275 grams of water increase if 36.5 kilojoules of heat were added? Okay?
Can we do this the same way?
We can. We can do this the same way. We know we have our mass of water, 275. We also know the specific heat, 4.184 joules for every gram degree Celsius. This is grams of water. And what is it we're after here?
The change in temperature.
Okay, so we don't know what the change in temperature will be, but that's what we're going to find out if we add 36500.
Why did you do that?
Well, see that they provided it in kilojoules and we want it in joules because our specific heat is in joules per gram degree Celsius. Follow that?
Oh yeah, I see that.
Okay, so that's all we have to do here. We just have to take the 36,500 divided by the 275 divided by 4.184. So 31.7 degrees Celsius is going to equal the change in temperature. Alright, so that's what that little triangle means. It's a change in. And we use the change in temperature, change in enthalpy, change in entropy, lots of different things that we'll use in the future.
Okay.
Okay, so a piece of unknown substance weighs 44.7 grams and requires that much energy to increase its temperature that much. I wonder if I cut this problem off. I imagine we're trying to find out what the specific heat of the material is. Okay, so we are given mass, 44.7 grams, and we're given energy, 2110 joules. We want to know how many joules per gram degree Celsius it requires, and the change in temperature, 23.2 to 89.86.
Is that just final minus initial again?
Yeah, 89.6 minus 23.2. We heated it up, so the initial was 89.6. Sorry, the final was 89.6, and the initial was 23.2. So 66.4. So 2110 divided by 44.7 divided by 66.4. All right, so 0.711. That's the specific heat. What material has a specific heat of 0.711 joules per gram degree Celsius?
Here is information from
Graphite.
owl.oit.umass.edu.
So here, I'll bring this over here so you can see. But this is a list of some of specific heats, and graphite has a specific heat of 0.711. So you see how we took a piece of unknown substance and we found its specific heat. There could be other materials that have that specific heat. It's not unlikely, but yeah, not going to be infinite number of materials that have that specific heat. Okay. Here's another scenario. What is the specific heat of the substance? Use the table 5.1 to find out what its likely identity is. Okay, so talk us through this one, Fred.
Me?
Yep.
Okay, so you got 8,460 joules.
All right.
And you got 437.2 grams.
All right.
And the specific heat is what you're after.
All right. What are the joules for specific heat?
The what?
Oh, the units.
Oh, joules per gram degree Celsius.
Okay. And what is the change in temperature?
We're going up to 68.9 from 19.3. So 68.9 minus 19.3.
That's right. So 68.9 minus 19.3. 49.6 is our change in temperature, or degrees Celsius, right? Okay, so 8460 divided by
437.2.
437.2 divided by 49.6. Okay, 0.390. What material has a specific heat of 0.390 joules per gram degree Celsius? Okay, so it looks like it could be let me bring up table 5.1. Alright, so table 5.1, 0.390, is that what we got?
Yeah.
So it looks like it could be copper, 0.385.
Okay, copper, maybe.
That's the closest at least. Alright, good. Next, an aluminum kettle weighs that much mass. What's the heat capacity of the kettle?
What's heat capacity? Is that specific heat?
So heat capacity is going to be related to a more complex system. Now this is not a very complex system because it's just a big piece of copper kettle, right? Isn't that what you just said?
Aluminum.
Oh, aluminum kettle. Okay. So it's just in a kettle and it's all made of one material. But we use the term heat capacity when we're talking about a whole system, usually when a system is made of lots of different things, right? So if I have a container where I'm going to perform a reaction, and the container, which we usually call a calorimeter, the container, maybe it is made of glass here, but it's surrounded by a steel container, and inside this area is a vacuum. Have you heard of those, flasks that you can buy, thermoses, right? It's not a new concept. For a long time they've been doing it. You pull a vacuum between the inner and outer layer of the thermos, and what that does is that decreases the ability for heat to transfer out or in to your substance. So you can fill it with something hot, and it'll stay hot. You can fill it with something cold, and it'll stay cold very easily because the thermal conductivity is really low through a vacuum. Right? So hydro flasks are the latest and greatest that do that. But if you drop your hydro flask, sometimes you'll hear a louder than normal pop. And you'll think, did I break my hydro flask? You'll look, you don't see anything. But what you likely did is you released air into that vacuum area. And so your hydro flask will no longer work. And you can tell that your hydro flask isn't working, right? How can you tell?
When you fill it with something cold, it gets wet on the outside.
That's right. The precipitate or the condensation of water on the outside, if there's something cold inside, is an indication that it's no longer, that vacuum is no longer maintaining the low thermal conductivity for the system. For a hydro flask like that, you wouldn't be talking about a specific heat because there's lots of different materials, and there's a lid, and if this was a calorimeter, you'd have a thermometer in here, and you'd have also an impeller. It's going to be stirring your solution, right? So you have different components, and all the different components are made of different materials and have different masses, and so you can't just find the specific heat of the whole thing, but you can find what we call the heat capacity of the whole thing. Units for heat capacity are going to be in joules for every degree Celsius that changed. Notice that specific heat was joules for every gram of the material that you change a degree Celsius. Heat capacity, though, is used for systems that contain lots of different kinds of materials. So to identify the mass of it doesn't make sense because it's just one system. It's not changing mass over time, right? Or it's not going to be different mass next time you use it. You're always going to have the same mass. So the heat capacity for this kettle essentially is the specific heat for it because it's all made of aluminum. But that's all right. We can call it heat capacity and just have units of joules for every degree Celsius. We're told its mass is 1.05 kilograms. I'm going to change that to 1,050 grams. Okay. The heat capacity, an aluminum kettle is what is the heat capacity of the kettle? So if we chose aluminum's specific heat, 0.897, that's joules for every gram degree Celsius, all right? Then its heat capacity, which we want to be in just joules per degree Celsius, is just going to be the product of those two numbers. All right, 1050 times 0.897. That's how much energy in joules it's going to take to raise the whole system 1 degree Celsius. How much heat is required to increase the temperature of this kettle from 23 to 99? 99 minus 23, that's 76 degrees. So I can just, this is again 941.85 joules for every degree Celsius. And if I'm going to raise it 76 degrees Celsius, then I just multiply those together, and that will leave me with how many joules of energy is required. So 71,000 or 71.6 kilojoules of energy. How much heat is required to heat this kettle from 23 to 99 if it contains that much water? With the density of that and the specific heat of that. So now we're going to be heating not just the kettle, but we're going to also be heating the water. So we have two things that we need to take into account. The kettle is going to require, what did we say?
71.6 kilojoules for every degree Celsius.
Oh, no. 941.85 joules.
Oh yeah, 941.85 joules for every degree Celsius.
941.85 joules for every degree Celsius. And that amount of water, how much is it going to take for every degree Celsius?
Well, we need to know the mass of the water.
Yeah, we need to know the mass of the water. We have 1,250 milliliters of water, right?
Okay, because it's 1.25 liters.
Yeah. And I get that to grams using the density?
Yeah, 0.997 grams for every milliliter.
0.997 grams for every 1 milliliter. Alright, so 1250 times 0.997, 1246. Alright, and we got 3, so 125, or 1,250 grams essentially. 3 significant figures. So 1,250 grams of water, 4.184 joules for every gram degrees Celsius. And what is our change in temperature?
Going from 22 to 99.
Alright, so that's 76 degrees. So I can either take the 76 here and solve for joules here, and take the 76 here and solve for joules there. Alright. Or I guess I could just do this and add it to what I got before, which was 71.6 kilojoules, right?
That's how much energy it took to raise the kettle that much.
Yeah, 71.6 kilojoules. So I'll just do that. I'll just take the 71.6 kilojoules from before, and I'm going to add it to what I get here for the water. So 1250 times 4.184 times 76. So did I do that right? 1250 times 4.184 times 76. Yep. Divided by 1,000 will get us into kilojoules. So 396 plus the 71.6. Alright, so 468 kilojoules, because it was 396 here, kilojoules. Alright, plus the heat for the kettle, so the sum of that is the total. Okay, good. How much will the temperature of a cup of 180 grams of coffee at 95 be reduced when a 45 gram silver spoon of that specific heat at 25 is placed in the coffee and the two are allowed to reach the same temperature? Assume the coffee has the same density and specific heat as water. Okay, so let's see if we can figure this out, all right? We've got a coffee cup. It's hot. We put a spoon in there, right? And the spoon at 25 degrees Celsius, it heats up, all right? The two are allowed to reach the same temperature. Assume the coffee cup has the same density as water. So we have 180 grams of water, essentially. Coffee is going to give us the 4.184 joules for every gram degrees Celsius. They said assume the coffee has the same density and specific heat as water. And the change in temperature for the, let's see, it's at 95 degrees Celsius. Okay. So we need to figure out how much that silver spoon is going to absorb. So we can see that the cup of water, the water portion, the coffee portion, right, has that mass and that many joules per every gram, right? And so if I take those two and multiply them together, 180 times 4.184, that is 753.12 joules, and for every degree Celsius. So that's how much the coffee is going to go down. That's how many joules the coffee is going to lose for every degree Celsius. The spoon is going to do what?
0.24 times 45?
Right. 45 is the mass of the spoon, and 0.24 is the what?
Specific heat.
Joules for every gram degrees Celsius. So it's going to 45 times 0.24, take 10.8 joules for every degree Celsius. Okay? So what we see here is this is how many joules it's going to lose for every degree Celsius. This is how many joules it's going to gain for every degree Celsius. So we can take the ratio there and say this divided by this and see that it's going to gain 70 times more energy in the spoon for every degree Celsius that changes. Alright, so you can then look at the initial mass of the, or initial temperature of the coffee, 95 degrees Celsius. And it's going to go down some amount. Alright, and the resulting temperature in the end, this side, the coffee, is going to be equal to the resulting temperature of the spoon, which starts off at 25 degrees Celsius, and it goes up some amount as well, right? And the amount that it's going to go up, the amount of X that it's going to go up, is going to be 70 times as the temperature is going to go up 70 times as fast because of this ratio of the energy, right? So 70x. And then we can just do math here and identify what x is. So 95 minus 25 here. That's 60 degrees. And then we have that equaling to 71x. I just added the x over there. So divided by 71, and that is 0.84. X equals 0.845 degrees Celsius. So about 1 degree Celsius is what it's going to change. All right, good. That's a good place to stop for today.